Namaskar my dear friends. Let's talk about gate driver. So we have reached in a situation where we can start talking about some simple circuits for some PFC power factor corrections or some power devices. So why don't we start with single channel low side gate driver IC with overcurrent protection features as well. Okay. So we'll talk about a IC from Infineon technology, which is a simple gate driver IC which is going to drive an IGBT. So our main purpose would be to understand how does a gate driver works and what are the features and details of this particular IC. If we understand one IC, we will be able to extend our concepts and exploration with other ICs as well. So this is the part number that I have utilized for explaining the complete concept about this particular gate driver, and it has integrated overcurrent protection feature as well as it has fault reporting and enable functionality. So if we talk about features in details, we can see it has overcurrent threshold with plus minus 0.5% accuracy, overcurrent detection with negative voltage input. We have single pin for fault output and enable both, like there will be FO as well as enable pin both. We have programmable fault clear time. Each and everything we will try to understand later. What we'll do is we'll try to understand this one. We have the logic compatibility of 3.3 volt, 5 volt as well as 15 volt. So any of the logic voltage level if you apply into the input pin, it will be able to work, and it has output in phase with input, right? Now we can see it has 3 kilovolt of ESD HVM, that is human body model of 3000 kilovolt, 3000 volt. Okay. If we talk about benefits of this particular IC, as I already told you, it has integrated overcurrent protection as well as it has only one pin for both the functions. One is that is fault output and enable function both. So it is going to save lot of cost and like a potential space that we uh, incur during the fault output and enable functionalities later on. As we have already told, overcurrent protection threshold tolerance is plus minus 5%, which is having a quite good accuracy for sensing the current, and it can take up to 25 volt maximum supply voltage to the VCC pin. So let's talk about the application where it can be used. So this gate driver IC can be utilized in our commercial HVAC, that is heating, ventilation or air conditioners. It can be also utilized in high voltage e-compressors, and it can be utilized in our home appliances. Home appliances is basically nothing but fridges, washing machines, all those things. Okay. We have power conversion, so in PFCs and all we can always utilize them, like power factor corrections and all, and we can also use in refrigeration and freezing systems. Generally these days people are going ahead with IPM, that is intelligent power modules, which includes all these gate driver, IGBTs and controller. All these parts will be together. That already I have been I have started you teaching this particular concept about IPM circuit design, but we are going to take about this particular gate driver in short. So what is the typical application it will look like? So let us say we have my microcontroller that is working with our voltage VDD. Let us say this logic level is 3.3 volt, and we have, let us say, one IO pin which is going to enable or disable this particular IC, which is the gate driver. Okay. At the same time, one IO pin will be there which will be working as PWM signal. So this PWM signal is going to the input of this particular IC, which will be giving the output, and this output is going to enable disable this particular IGBT. So this is my IGBT which is being driven by this particular gate driver. So why do we need gate driver in the middle? This PWM could have been used directly to drive this particular IGBT, but the reason is it does not have the capability of that much current and that much voltage levels and all. That's the reason we utilize in between gate driver. Okay, so this is also called as gate driver. And there are two kinds of gate driver. One will be like high side gate driver, one will be low side gate driver. So we are right now talking about low side gate driver, where we will be driving the lower MOSFET or lower IGBTs. and this is the rectified input that is coming from the bridge rectifier and everything. So let us say this is my AC input. After all uh, protections and safety features and all those filterings and all, we are going to get after bridge rectifier the rectified output, and this is going to come up as input here, and this is how we are going to rectify the output and get our proper output signal at this particular place. Okay, and it has inbuilt feature of overcurrent protection also, where we are going to monitor this particular current sense resistor, and this is how this particular IGBT current is going to pass through this current sense resistor, and it will give us the overcurrent protection feature as well. If you talk about quickly a block diagram of this particular gate driver IC, we have, as you can see, we have supply pin which is going to have under voltage lockout and filters, all those options. We have enable pin which is going to have a pull up resistor here, and this is how it is going to have a schematic trigger. So this is one schematic trigger which is going to enable my PWM disable logic or enable logic, all these things properly once it gets a high signal. So basically we'll be directly connecting it to my VCC, so that is more than enough. Okay, at the same time this is my input signal which will be having a controlled PWM signal which is going to control the output pin which is going to drive our IGBT. And as you can see, we have push pull operation here which is having two MOSFETs. One is like N channel MOSFET and one in P channel MOSFET. So this is also working as push pull method, and this is how it is going to drive my IGBT. And that's all. It is having one overcurrent protection technique which is going to enable, check the using this particular comparator, and this particular comparator will be giving the fault output signal which will be taken out at the fault pin as well. So this is acting as enable pin as well as it is going to give us the fault signal both. If we quickly see again the pin configuration, so as you can see, the OCP pin is actually called as current sense input pin. It has common pin as ground pin, it has out pin as gate driver output, it has VCC pin which is supply voltage output pin, supply voltage pin which is the main supply voltage for this particular driver, and it has enable and fault output pin, and it has input pin which is going to take the PWM input which will be trying to give you the gate driver output phase. So let's open the data sheet quickly and try to understand what are the other different functionality about this particular gate driver. So as we have already discussed about the features and the benefits of this particular low channel like single channel low side gate driver IC. Now if we move next, we have already talked about the typical application that we have seen regarding this particular gate driver IC. Ordering information is this is in this package which is SOT23-6 package. So basically it is a 6-pin gate driver IC, and this block diagram we have already seen. Now coming back to the pin configuration, so just now we explained you what were all the pins and what is their functionalities, and this is how it is arranged in this particular fashion of just 6-pin IC in SOT23 package. Now let's talk about the truth table. So truth table is going to give us the understanding of input and output. So let us say my input is low, so definitely my output will be always low. So there is no question about that. When input will be high, then we have some condition in the middle, and accordingly my output will be high. So what is that? My under voltage lockout pin should be high, output overcurrent protection should be low, like it should not be receiving a signal that my output is, or my like IGBT is stressed to overcurrent, so it should be low, and then my enable pin should be high, and this is how you are going to get your high at the output. Okay, rest others are no conditions, so you will see always output as low. So don't care conditions will be happening based on the under voltage lock output pin or overcurrent protection or enable pin. If it is low, then nothing can happen and you will always see output as low. Now moving to the qualification information, so that's nothing but like we have ESD and like it is charge device model and human body model. So how much is the like qualification. So if you see CDM model, that is charge device model, is 1.5 kV. Human body model is 3 kV. It has IC latch up test of class 2 level A, and other functionalities like qualification level is having, like ZDC industrial qualification as well as consumer qualification level is granted by extension of higher industrial level. And if you have to have about moisture sensitivity level, then this will be taking up MSL1 at 260 degree centigrade. So these are all qualification information which is making sure this particular IC is applicable for utilization in our consumer applications and industrial application as well. So the application already we saw what was that. Coming back to the absolute maximum rating, so any ICs that you have already seen, or till now I have been giving you the explanation about any ICs that we have taken into account. We have always seen what is the absolute maximum rating for the particular uh, IC. So we can see the VCC can be taking maximum 25 volts. You have to make sure the VCC pin should not be stressed more than 25 volt, otherwise it will get damaged. The output pin will be having VCC plus 0.3 volt. Okay, and you can see we have voltage current sense pin which will be also taking VCC plus 0.3 volt. Let us say voltage at enable and fault reporting pin will be also VCC plus 0.3, and next logic input will be also taking VCC plus 0.3. So let us say we have voltage 12 volt at VCC, then this will be like a good system. We can also work with 15 volt system or something like that, but do not go ahead with more than 18 volt system. Okay, we'll talk about the power dissipation capacity, then this is 0.5 watt. And if you talk about thermal resistance junction to ambient, this is 250 degree centigrade per watt. So for 1 watt of power dissipation across the IC, the temperature increase will be by 250 degree centigrade. So anyway, the capacity itself is 0.5 watt, so it will not be increasing much. If we talk about recommended operating temperature, so recommended operating conditions, then you can see the VCC must be maximum 20 volt or less than this much, and minimum is 12.7. So it will much more suitable for your 15 volt system application. Okay, the output voltage is common to VCC. So whatever VCC that you are going to give, that much will be your output voltage, that is going to be the gate driver output voltage. We have voltage at current sense input pin, that is also going to be VCC, and all other pins we already saw, that will be VCC. The ambient temperature that it can work up to 125 degrees centigrade. So hope you are able to understand how to read the data sheet properly and very patiently, and each and every parameters we should have in our hand. Then only we can become the very good designer of our hardware engineering systems, or like any kinds of electrical and electronic system to design at our hand. If you talk about static electrical characteristics, so static electrical characteristic is nothing but, let us say my VCC is 15 volt and ambient temperature is being considered as 25 degrees centigrade unless it is otherwise specified. Okay, so these are very simple. We have supply under voltage lockout pin is going to be 11.9 volts, so it will not enable, like the system will not start unless my voltage has reached up to maximum 12.7 volt or 11.9 volt. Okay, like if you give 10 volt at the input, then it will not start because the voltage supply required was 15 volt, so minimum is required is 12 volt, then only it will start. That's the meaning. So similarly other all symbols and their definitions are given, so that we are not going to discuss about right now. It's very straightforward. Dynamic electrical characteristic is also same thing, like what is the turn on propagation delay, what is turn off propagation delay, what is the rise time, fall time, what is the disable propagation delay. If you are going to disable, so all are in nanosecond range, and you have fault clear time, so that is in microsecond, which is going to be 103 microsecond typical time. Coming back to the application information, so this application information, like can take up what are the other things that you can see here, like it has IGBT gate driver, it has switching and timing relationship, it has a logic input compatibility or compatibility, and under voltage lockout protection and over current protection. So all these things we have already seen in this particular IC. so we'll not consume our time in this particular thing. Let's directly get into the typical application that we will see. Okay, so let us say this is the simple board application that we can see here. So it has, as I already told you, it has AC input, and this is after bridge rectifier it is shown. This is my bulk capacitor that is at the input, this is the inductor that is there, and this is my IGBT which is going to be driven to give you the rectified output at the output voltage. Okay, so this is how this is going to work. So this is also called as rectifier diode. Okay, now this is the RCS, which is going to be our current sense resistor, which will make sure like how much current is flowing through the uh, collector terminal of the IGBT, and this is how this is called RC filter at the OCP, that is overcurrent protection pin, and this RC filter will make sure the filtered signal goes into the overcurrent current protection pin. If you want, you can put one amplifier as well here. So this amplifier, or like a amplified signal, will go into the OCP pin if my output signal is very small. The other part you can see, we have VCC supply, and we have enable pin that is going to get enabled by my microcontroller supply voltage itself, which is taking the supply voltage here. And this is IO, which is going to give you the output as fault pin also. So as you can see, the understanding is like this. We have a pull up resistor because of the fault pin was open drain pin. So open drain pin must be pulled up, and pulled up is at the voltage of microcontroller voltage logic level. You should not connect it to VCC because VCC may be 15 volt. So as I told you just now, it is 15 volt. So 15 volt logic level should not be pulled up. It should be pulled up to VDD, that is 3.3 volt, and that is going to give you the output of fault signal also at IO signal. So once it is high, it will enable this particular IC, and that job is done. Now if there is some fault or some signal, then it will act as a output signal, and this output pin will be giving the signal at the IO pin. And this is my PWM signal pin, which is IO1, which is going to give you the PWM signal at this input, and this is how the gate driver is being driven, right? Good. So moving back to the next, yeah, if you see the timing diagram, let us say this is my input pin, which is going to be my PWM. This is my output pin. So what will happen? This is my at the IGBT gate. Okay, IGBT gate pin. So this gate driver is going to receive, whenever this is high, this will be receiving high after a little of delay, which is in microsecond, and as soon as it goes low, the gate will be pulled low, right? And then you can see again, if it is going high, so it is going high. So this is how it is working properly. And overcurrent protection, you can see that overcurrent protection, as soon as it goes high, it will go low, because it knows that if there is no problem with the overcurrent, then it will be always will be in the range. Okay, so this is how it works. And fault pin will be going low when there is a like a fault. So this is, if there is any fault or something, then only there will be fault signal triggered, otherwise it will be always fault off. Okay, so fault off is actually high, and whenever there is a fault detected, then that will be considered as low. So you can see fault is active low. So whenever fault pin goes 0 or goes low logic, then we will consider the IC is in faulty condition, and that has happened because overcurrent protection would have increased very high value, or like an irregular value. Good. So enable pin we have already understood, and fault pin we have already understood. So that's all. So this was all about this particular IC, which is we have just now seen, the gate driver IC. Now coming back to the application that we have seen, so we saw just now pin configuration, then we saw this typical application also, and then if you talk about the evaluation board that they have already designed, so this is the PFC board that they have designed, and this is our eval board, which is there as a adapter, and this adapter is going to get connected to the 3 pins of the IGBT on the PFC board, and that is going to be driven. Okay, so this is very simple board which is going to be used in a PFC board. Okay, So if you see the circuit that was designed for this particular gate driver, so this is my gate driver that we had just now discussed about it. Okay, so what is happening is this is going to be in my microcontroller pin. Okay, so this my fault output will be there, and as you can see it is connected directly to VCC now because VCC is there here. This is my PWM pin. Okay, and this is going to drive my gate of this IGBT. So this is how IGBT is being driven Q1, and these are all snubber circuit, which is you can see like RC diode is there and resistor is there. So this is acting as some snubber circuits which will make sure the gate doesn't go, like have a spike or something like that at that at any particular moment. And that's all. And this is my OCP, which is connected to 0 ohm resistor, and this 0 ohm resistor is getting connected to my OCP. So I'll tell you how it is connected to the next board. So we have 5 pins that is there. One is like OCP, one is COM, that is ground, and one is VCC, which is going to be the supply pin, which is we have fault output pin, and we have PWM signal, we have gate, and like emitter, and one more pin, 3 pin will be there. So we'll see that directly here in the data sheet. So let us say this is the evaluation board that I am talking about, okay, which we have just now downloaded from the like eval board of 1ED44175NO1B, okay, N01B. So as you can see, we have this particular like block diagram of the PFC board and adapter board just now I was talking to you. Okay, so this is all about this particular gate driver that we have seen just now, and hope you have now a very good understanding about how this particular gate driver IC was working and what are the things that we have to always like take into account. It's a typical circuit that if you want you can see, or its pin configuration and all those information that you can very quickly see and try to understand how we can design our required circuits. So anyway, with moving on these things, what we'll do is we'll try to explain more complex ICs. Let us say we can explain about UCC28C44 or UCC28C55. Okay, so these two ICs there in my mind, so that you can become very thorough in gate driver design, or like flyback converter design, or all those kinds of like basically controller PWM controller design. So these are all called as PWM controllers. Okay, so in PWM controllers functionalities, you will understand that how my PWM is being controlled, and this is enabling the gate of the MOSFET. Either it can be a MOSFET, it can be a MOSFET connected to my primary of transformer. Okay, and this is how it is going to get like enabled, disabled, or being controlled at the output, so that you can get your flyback converter at the output, or all those things. So either it can be MOSFET or IGBT or anything is there, and it is going to get controlled by the PWM that is coming from our microcontroller or any kind of controller, whether it is DSP controller or any other type of controller. So hope you have a good understanding about this particular gate driver and how to design a particular circuit that is there with our project or our challenge in our problems. Thank you so much guys. Bye.